Here are a couple useful formulas. They are useful for modeling things that grow exponentially or decay exponentially. Decay just means it's a fancy word for decrease when we're talking about exponential functions. You'll notice that the two formulas are almost identical. The only difference is that the exponential growth function, we are doing 1 plus r, and the exponential decay function, we have a minus sign, so we're doing 1 minus r. Okay, and in both equations, y, a, r, and t all represent the same thing. So y is the final amount, a is the initial amount or the starting amount, r is the rate. So if it's exponential growth, it's increase. If it's exponential decay, it's a rate of decrease. And then t is the amount of time that has passed between the initial amount and the final amount. So here's what one of these functions looks like. This is the growth function, so I called it g, this green one, growth. And I chose some values for a and r. So in this case, I chose a to be equal to 1. So the initial amount is 1. And you can see that here, that the graph, when x is equal to 0, y is equal to 1. So the starting point of this function, or you can think of it as the y-intercept, is 1. And then I chose r to be 0.2, which means the rate of growth is 20%. Okay, so you can see the function here. Now, it's worth thinking about what happens when these numbers change. So notice what happens when I change a. If I change a to 3, for example, notice the function still has kind of the same shape. It still has this upward curve, but now here it has a y-intercept at 3, so the starting value is 3. I can also change r, so I can make r bigger or smaller. I'll make it bigger, and you'll notice as I make r bigger, in this case now it's 60%, you can see that the curve is much more steep. And that makes sense because if you increase the growth rate, you would expect whatever quantity you're looking at to grow more quickly. Okay, here I've got the decay function. So here I've got d for decay. Notice the shape is kind of similar, except this time it's kind of reflected across the y-axis. So instead of growing, the function is decreasing. As the time goes to the right, the function is getting lower and lower. Okay. And again, we can change the y-intercept or the starting value by changing the value of a. So if I make a equal to 6, now you can see the y-intercept here is at 6. And if I change the rate of growth, so if I make the rate of growth larger, like 40% now, 40%, the curve got more steep again. So it's decreasing more steeply, or you can say it's decaying at a greater rate. And finally, let's look at some real-world applications of these concepts of exponential growth and exponential decay. And what better real-world situation than the global pandemic that's happening right now in spring of 2020. So I am going to take away some of these countries because I want to make some points here. So okay. And let's get rid of France as well, and Australia. So, can you see any exponential looking functions here? If I'm looking at Brazil here, it definitely has that kind of steep upward curve to it. So does India as well, but India seems to be curving upward less steeply. So one thing, if you're thinking about those two formulas we were just looking at, you might think that they're both increasing exponentially, but Brazil has a higher rate of increase. And you could actually calculate that by going day by day and checking what is the rate of increase. Another thing you can do to make these graphs a little bit more clear is we can do what's called a 7-day rolling average. You'll notice that there is some kind of bumps up and some bumps down in this graph, so it's not perfectly smooth. It doesn't look as much like an exponential function as you might want. So the 7-day rolling average averages out 1 week at a time. And what we get is we get much nice, smoother functions. And there's lots of reasons why those bumps are there. One reason is because in some countries, fewer people are working on Sunday, for example, so then fewer cases will get reported because there are less healthcare workers working. There's lots of reasons. That's just one reason. So the 7-day rolling average helps to smooth out some of that data. Now, you might look at Germany and think, well, that's not exponential because look, it kind of curves upward and it gets flat for a while and then it curves downward. So that's some other kind of weird function. What's kind of interesting is we can change the date here. So if you went back to look at Germany and you just stopped the graph on this date, which is April 4th, this purple line here does look exponential. So at one point, it looks like Germany was having exponential growth, right? It has that kind of upward curve that's getting steeper and steeper. What happens is over time, they managed to decrease the growth within their country and flatten things out. So let's take one more look at that. Instead of looking at total confirmed cases, let's take a look at the daily cases. So if I look at daily cases for Germany, I'm going to take away India and Brazil. Look at what we've got here. So you'll notice that now the function is decreasing quite steeply at first, and then it kind of starts to flatten out a little bit here. So this actually, if you were to ignore everything from this point earlier, so if you were to ignore all of the data before April 10th and just continue from here, it kind of looks like we have exponential decay here. So in other words, the new cases are decreasing at a steady rate.